Okay, welcome to the fourth class meeting. We are going to continue this paper. So last time we stopped just before we convert each term in the objective function one by one in the frequency domain in terms of the vectorized Fourier transform. So let's see the first one. So here, this is the first term, expectation of the case symbol. And here, the sequence B of K is modeled as a Weiss stationary random process with mean 0. And I remember some other assumption. Yeah, just a second. Okay, so yeah, this is the only assumption. Now, in the time domain, we define the autocorrelation function, assuming this BK is complex valued. Then it is defined as B of M times B of N conjugate. Our convention is that we put the conjugation superscript on the right side of the product. So this is the definition. And since we assume Weiss stationarity, there exists a single variable function, misleadingly named using the same name, R sub BB. And our convention is that we subtract from the left argument the right argument, so m minus n. Now, Weiss stationarity means that if we define its Fourier transform, then what happens? We have some function. Here, we are going to call it m of f, which is the discrete time Fourier transform of the autocorrelation function. Got it? And this term, which is same as the case second order central and non-central mean, is what is first in the time domain, R sub BB of 0. Because this can be viewed as B of K times B of K conjugate. So we have K minus K, which is 0. So this is that value. And here, this is also called M of 0, as we've just seen. Now, this is in the time domain. What about in the frequency domain? So here, we have the relation between this R sub BBL and M of F. And using the synthesis equation, what can we do? We can actually integrate this M of F e to the negative j 2 pi f, let me say FL df evaluated at L equals 0, means we have the integration of this power spectral density over the period of length 1. However, here comes the trick. We are rewriting this one in order to replace the integration upper and lower limit to plus minus 1 over 2t. Then, using the change of variable, you can easily show these holes. Got it? So, in every integration in the frequency domain, we are going to use the integration interval negative 1 over 2t to 1 over 2t. Got it? So we have done with our first term. Now, what about the cross term 9b, which is this one? Last time I asked you to derive these lines so that you know why we have this real part operator. In case you didn't do my homework, let me just derive it by expanding some z minus a absolute value squared. So we have z minus a times z minus a conjugate, and we have z minus a times z conjugate minus a conjugate, everybody knows. And then we further expand zz conjugate and za conjugate, az conjugate plus aa conjugate. And here, the first term, zz conjugate, is nothing but z absolute value squared. And the second and third term can be written as this one. And the fourth term is again, right, like this. And everyone knows that the real part of some complex number b is what? B plus b conjugate. So we view az conjugate as b, then we have z 2 times real part of za conjugate, or if you want, z conjugate a plus a squared. Got it? That's why we have this real part operator. Now, we want to rewrite this cross term. And what do we have? So here, the proposition claims that this negative 2 times real part of expectation of bk conjugate times zk can be written this way. So basically, if we ignore these negative 2 real parts, we are going to show that expectation equals finite interval integration of what? Of this product. And it may looking complicated, but if you view this enclosed part as a vector valued signal, it's simply an inner product between wf vector and m times p vector. Got it? So let's see how we end up with that one. So here goes the step-by-step derivation. So first, we find that z, which is the sampled value at the receiver with time index 0, L equals 0, can be written this way without shifting the received waveform relative to the origin. So there is no t minus L capital T because L equals 0. So we have this one. And we know from the definition of z of t, we have what? This z of t is nothing but what? Sigma b L st minus lt plus n of t, right? Sorry, convolved with h of t. And we defined in some line this transmit filter impulse response convolved with the channel impulse response as p of t. So we have sigma b of L, p of t minus lt. If we want k, then let's use k. Okay. So first we have this summation over k, right? This V0 conjugate and Bk means what? Expectation of B of k times B of 0 conjugate. So which is the autocorrelation of B evaluated at k, which is denoted also by M of k. So this is autocorrelation function. And then we have integration. And we have dt. And what do we have? We have actually this times not only this one, this times that one, but we assume that noise is independent of the signal and of zero mean. So this is ignored. Then we eventually have W of t conjugate times P of t minus kt. That's why we have the integrand here. Got it? Then we use the pairwise relation. So first we convert this time domain integration of the product into the frequency domain integration of the product of each term's Fourier transform. So if you remember correctly, the general version of pairwise relation is what? Inner product in the time domain is the same as the inner product in the frequency domain, right? So this becomes x here. So what is this one? Capital P of f e to the negative j 2 pi kt. So we have this one. And we have W of f conjugate. Sorry. Yeah, this is W of f conjugate. So here and that. Got it? Confusingly, I used the parameter xi here. And then let's see. From here to there, what have we used? We used the definition of dTft. So this summation and m and this e to the negative j 2 pi xi kt is nothing but the discrete time Fourier transform of the autocorrelation m of k evaluated at not just xi, but xi t. Got it? So we have this. So we have integration w, p, and m of xi t dxi. Got it? And so far, we worked in the continuous frequency domain. Now we are going to convert this one to the finite length interval in the frequency domain from negative 1 over 2t to positive 1 over 2t. So basically, the next step would divide this one, this interval, into so-called Nyquist zones. And the ordinary Nyquist zone is defined as the interval from negative 1 over 2t to positive 1 over 2t. By shifting the center by integer multiples of 1 over t, you have another Nyquist zones. So this integration can be written as many, many integrations in different Nyquist zones. Got it? So you divide the interval. And then, interestingly, if you rearrange, then you get this one. Got it? And here we use the trick that M of xi is periodic with period 1, which means capital M of xi t is periodic with period 1 over t. So any shift by integer multiple of 1 over capital T for capital M of xi is the same because it's periodic. We used that part. So here, this just comes out, and then we have this one times that one divided into different Nyquist zones. Then by using the vectorized Fourier transform of P of xi and also W of xi, we have the inner product. Got it? Like this. So capital M is scalar valued, not the matrix valued. Be careful. So we have converted the cross term using the vectorized Fourier transforms of the received waveform and the overall transmit waveform, which means the transmit waveform convolved with the channel impulse response. Now, we have the third term, 9c. And this is let's work on it. Let's work on it. So now it becomes more complicated, but it's not that difficult. So the claim is that this term here, again, due to the cyclostationarity, we don't need to focus on general case term. You can show that all these terms are the same value due to the cyclostationarity with capital cycle period capital T for any k. So for convenience, we set k equals 0. And the claim is, again, interesting. So again, we have integration on a finite length interval, the Nyquist zone. But now we have a so-called quadratic form. Just ignore parenthesis f, then you have something like this. And here comes what? Even though it's a rank 1 matrix for each f, because it's an outer product of a vector p times scalar. But anyway, you have Hermitian symmetric positive semi-definite matrix here, even though it's rank 1 in this problem. Okay. Later, in other papers, you will see this Hermitian symmetrical positive semi-definite matrix is of rank 2 or rank higher than 1, depending on your signal model. Anyway, so this is very interesting in the sense that this is the desired signals, kind of desired signal parts power, right? Because we subtract the noise component. And this desired signal is what? In the time domain, it consists of data modulated, time shifted P of T signals, right? And there is no signal else. And this signal appears here as a rank 1 matrix. And in the receiver, you have W of T that encloses this signal part before and after. Got it? And you have the eventual signal part power. And again, first, we work in the discrete time domain. So we subtract n of 0 from z of 0 to have this term. And it's nothing that difficult. And again, we expand this one using that property. Modulo square over complex number a is a times a conjugate. And then we expand and we take the expectation, and expectation works only on what? Works only on this B sequence. So we have what? Again, the autocorrelation function of this Y sense stationary discrete time random process B. And its autocorrelation is defined as M. And this part is confusing, but since this B sequence is not uncorrelated, the elements of B sequence is not uncorrelated, you have countably infinite sum, which relates the L symbol and L prime symbol effect. So you transmit effectively P of T pulse by shifting it. The problem is that the data multiplied to each delayed version, they are correlated in general. Of course, under certain conditions, you can just have only one term. In that case, M of 0 is some constant and all other M are 0. But this is general form. Anyway, so here, what is Q? Q is the time autocorrelation function of the overall pulse, which is a common exercise in matched filtering. So you have transmit pulse P, and in the case of the use of matched filter, you are going to use a filter with impulse response P of negative T conjugate. And that appears here. Since we may not use matched filter, but still, theoretically, the term can be written as kind of autocorrelation function modified by W of T. Anyway, so this part shouldn't be that difficult to derive when you work on yourself. So I will ask you in the probably exam, derive every step, okay, without looking at any crib sheet or something. Anyway, so far so good. And now this is what? This is a product of two sequences. And here goes pairwise relation for discrete time signals. So suppose you have X of n sequence and Y of n sequence, sum up for all n. Then what would be the frequency domain in a product in terms of their discrete time Fourier transforms, right? And if you remember correctly, your integration interval is from one period of length 1 in general. And here comes the DTFT of the first sequence. And here comes the DTFT of the second sequence conjugate integrated over this period. So let me see. So yeah. So here, X corresponds to Q of L, T. Got it? So XL, if you want. Let me use L is the parameter. So LL. Yeah. Something like this. So XL corresponds to Q of LT. Be careful. Q is a continuous time signal evaluated at specific time instant L capital T. Then you have what? A discrete time signal, XL. And here, be careful, K is a fixed value. L is the time parameter. So YL is nothing but Q of L minus KT. And the Fourier transform, discrete time Fourier transform of this sequence is what? What is the sampled values discrete time Fourier transform? This is a very important result for every communication engineers. So let's derive it if you have forgotten. So in signal gen systems and digital signal processing of your undergraduate courses, there was some very simple lemma saying this: given a continuous time signal, let's call Q of T for our use in this proposition. When X of L is defined as the sampled version of Q at every capital T, then, so by the way, we are assuming that the CTFT of this continuous time signal Q is capital Q. Now, what we are going to derive is that our DTFT of this discrete time signal obtained by uniform sampling is what? Anybody? Anybody can fill up this part? Now this is sampling theorem, right? So you have the sampling rate and folded spectrum. And that folding possibly have infinite terms, countable infinite terms, depending on whether Q is band limited or not. Now you have what? This signal Q is scaled so that 1 over T can be translated to xi. But that's too confusing. So let me put T here to make everything simple. In that case, we can just shift this one. Done. Okay? So be careful. Usually this does not appear in the undergraduate textbook, but we just replaced F with xi. In that case, we can just simply fold the original spectrum using integer multiples of our sampling rate. Got it? Now, here, again, we may rewrite this product in the frequency domain as this one. Here, the trick is that we have 1 over T. Integration interval is now over length 1 over capital T. And you have capital T instead of, you have xi T instead of just F of original or xi of the original integration. Got it? So we are going to use that trick. And here, the first term is simple. Second one may look complicated, but you can still do that because delayed version has the Fourier transform. That is the original Fourier transform times e to the negative j 2 pi f delay, right? You know that. And by combining these ideas, first, you can end up with this integral first, and then again, dividing the interval. Amazingly, you have this result. Ready? So you work on it. You yourself once must do it yourself. Okay? Not just using eyeballs, but using your pencils and papers. Otherwise, you will never understand. You derive it yourself. Got it? So we are almost done. Now, the last term. And this term is rather simple. It looks simple, but actually it is not, because we assume that the noise, capital N of t, is cyclostationary. And here comes the highlight of the property. So N of 0 is nothing but capital N of t times W conjugate of t dt, right? And again, we use the trick that be careful, you have to use different integration variable or parameter. So let's use S. Ready? Then here we have deterministic functions W and random functions N. So we have integration, double integration with W, T. And we call this autocorrelation as this one. And we have this time domain kind of quadratic form. Okay? It's very similar to, as I repeatedly told you, the quadratic form W Hermitian RW, right? It's already look like that, but it's a double integration in two-dimensional time domain. So we need more work to convert this double integration to a single integration over what? A frequency domain, especially on the Nyquist zone. Right? So we need some steps, and eventually we will end up something like this. And I expect we have something like this. And here comes, very interestingly, a matrix valued power spectral density. And what is this single parameter function? Why we have only single integration, even though we started from double integration? That is related entirely to the title of this course. cyclostationary random process has a very special correlation structure in the frequency domain. And that makes double integration converted to a single integration. It's probably you've seen something similar when you derive what? When you derive some results using delta functions already. Sometimes if you have delta function, integration just becomes some evaluation of a function, right? For example, suppose you have some signal x of t multiplied by shifted version of Dirac delta and integrate over entire real line. Then what do you have? You have x of t0, right? Because this t disappears after integration, and you have x evaluated at t0, right? Something similar happens here, and this is very, very interesting. Let me provide you some upside down viewpoint. Uh-oh, I didn't put it here. Okay, probably I did it in some other paper. Okay, got it. So let me just follow my derivation a quarter century ago, step by step. So the idea is like this. First, your double integration, your quadratic integration of a quadratic form in the time domain is in general, converted this way. Here, interestingly, the first one conjugate is converted to its Fourier transform conjugate. And last term is transformed to its continuous time Fourier transform. And here, the mid term, it may called kernel in linear systems, or anyway, two variable function is converted to the two-dimensional Fourier transform. Then what is the two-dimensional Fourier transform of a general complex valued signal? And we define this way, but some people really hated this notation. They said this is not double Fourier transform. This is so-called symplectic Fourier transform. And probably you've heard it when you studied OTFS. Do you remember? So let me remind you what is the double Fourier transform for general real valued signal and else. So first, remember the definition. Suppose you have real or complex valued continuous time signal x. In that case, its Fourier transform is what? Is to find its component with Fourier frequency f. Be careful. Frequency is, to elementary school or middle school students, are defined as the inverse of period. When we talk about Fourier basis or complex exponential function, e to the positive j 2 pi f capital T and e to the negative j 2 pi f capital T has same period. If period is defined as what makes the signal same with minimum positive number. And if frequency is defined as inverse, they should have the same frequency. But in Fourier analysis, we put the sign. So sometimes frequency is negative, right? Now, this is the definition. And for some r, t, comma, s, usually they do this one. So they just take this idea the same. So we are going to take the component in this signal for the t variable, the frequency positive f1. And for the s variable, frequency positive f2. That's why usually double Fourier transform has negative signs in the exponent. Got it? For the symplectic double Fourier transform, we do a little bit differently. Because the signal of two variables is usually obtained not just given as any arbitrary two variable function, but given us as a kind of autocorrelation function type thing, which is computed what? Multiplying signal and its delayed version with conjugation. So the S variable is kind of already has conjugation. So if we want to take out the F2 component, we need what? Positive J2 pi F2S dt ds. Got it? That's why I use symplectic double Fourier transform, not the ordinary double Fourier transform. But I called it double Fourier transform, and some reviewer didn't like it. Anyway, so as you see here, for variable t, we have negative sign. For variable s, we have positive sign. Got it? And this is intentionally chosen. So its inverse Fourier transform is also actually symplectic to the inverse transform. So we have plus sign here and subtraction inside the parenthesis. This is very, very confusing, but very important in our derivation. And the choice of these signs are very important. So it may appear in your midterm and final exam. So I suggest you to derive every step of this paper. Then we may have a bullet train in the review of next papers, because almost the same formula appears again and again with increasing complexity. Some of you have already printed out the next papers. Then we have multi-user case. So our received signal, not only a single QAM signal, it's a summation of multiple QAM signals. And each signal is a cyclostationary random process. In that case, our signal minus noise itself has what? Quadratic form, now with rank capital K, which is the outer product of each signal's rank 1 matrix, something like that. And also, in order to model other cell signal, which may be again cyclostationary, because usually we have same standard, wireless standard in our cell and next cell in cellular system. In the case, adjacent cell interference may have the same cycle period, even though the signal may suffer from different linear time invariant channel. So in that case, desired signal is a summation of cyclostationary rank 1 signals. Interference is also in that form, but in that case, since we have no control about other cell signal, we may just assume that it's a cyclostationary interference with the same cycle period. Got it? So this paper is very simple Some of you say that it's too complicated, but you have to derive every step, at least here at once. Then the next papers would be very, very straightforward, and we may pace up the speed in covering all the papers listed in the reading list. Anyway, so by using this double Fourier transform and inverse transform, we can kind of show this what? Two parameter signals pairwise relation, kind of, right? So it's a product of three signals, but it's a kind of quadratic form with double integration. Now we have kind of quadratic form. It's not exactly because this and that can be in general different in this form, but we are going to use same signal and same signal here. So anyway, we have general result for two-dimensional signal. Now, this result will be applied to our case to derive the last term, which is the expectation of absolute value square of n of 0. Got it? So this is the first claim, and this is not that difficult because as I already have derived what we have the time domain integration of this quadratic form, right? And applying this result, we immediately have two-dimensional integration with now double Fourier transform of the autocorrelation function of a cyclostationary signal. Actually, this double Fourier transform has a very interesting structure. That's why we have single integration eventually with finite length Nyquist interval appearing in the integration. And we have vectorized Fourier transforms and some strangely named matrix valued power spectral density of the noise signal. To derive this one, we are using the lemma in the reference 15 of this paper. And here comes interesting thing. Suppose we have two variable function, but it's not just two variable function. It has spatial structure. The function evaluated at t comma s is the same as the function evaluated at t plus some offset and s plus the same offset. And this is actually the property of cyclostationary random processes autocorrelation, as you've seen last time. Do you remember that tile copying for the main diagonal, which is actually even conjugate symmetrical for random process and something like that? And here, this is unnecessary but appearing in my old paper. And by introducing some signal, continuous time signal, with superscript k, I didn't introduce that superscript, the original paper. So actually you have countably infinite continuous time signals of single variable, right? Parameterized by k. Now, this two-dimensional function can be written in this form. And you may say that it looks familiar, right? What is it? It's a Fourier series representation of a periodic signal. Let me remind you, suppose you have a continuous time signal that is periodic. So R of t equals R of t plus k capital T for all t. So Do you have the same property? So the idea is simple. We view this one as a function of t temporarily with s fixed. Then it's periodic in t. So there exists a Fourier series for each s, right? But anyway, is it k? Okay. So you have something like this. Am I right? A sub k is called the Fourier series coefficient for the complex sinusoidal signal with frequency 2 pi k divided by capital T. Am I right? Now, let's take a look at this two variable function as a single variable function. Then just copy and paste R and small t s to ignore its existence. Then we have Fourier series a k and s, right? E to the j 2 pi kt or capital T, something like that. The problem is that this should be dependent on the choice of s, and s is a continuous parameter. So let's just use the parentheses. Ready? And now let's compare these two. Something's different? Yes. Why? Because here we are not just Fourier transforming like this. We define R tilde this way. And you are familiar with that one. It's a trick when we handle autocorrelation function. If I write it again, probably I would write that this way. But anyway, at that time, I just followed the original convention. Okay. Anyway, so after defining R tilde this way, and we view R tilde as a periodic function in T. Got it? That's not that difficult. Anyway, still periodic. And we expand this R tilde T tau using the Fourier series. Again, I recommend you derive this one. Got it? So you have interesting property like this one. And what does this mean? What does this mean? If we view R as the autocorrelation function of a Y-sense cyclostationary random process. We've already seen last time, if we plot the level sets for the autocorrelation function, what happens? You have the same tile appearing again and again in the main diagonal, and off diagonals are the same, something like that. So I draw the repeating mountains last time. And now let's draw a auxiliary line so that we have what happens. So suppose we follow this line, and this line is can be parameterized by a single parameter, possibly tau. Why? Because on this line, S equals T minus some value, minus 0.3 over capital T, something like that, right? So they have same time difference. Now, we follow this line by changing the variable t. Then what happens? You have a periodic function. Actually, we are utilizing this property of autocorrelation function of cyclostationary random process. Given a fixed offset between t and s, t minus s, you have a periodic signal when you change t. Got it? Now, we expand this periodic signal using Fourier series. That's what we have here. Got it? So, whenever you have some strangely looking theorem, proposition, lemma, try to visualize. Got it? This is very important. Otherwise, you will get lost on in the middle of nowhere. Okay? Anyway, so it's not that difficult to see this periodicity if you draw other lines, right? Got it? Now this makes sense. Why the authors replaced this RT comma S to have single delay parameter tau. Got it? Because these lines have same t minus s values and periodic in t. Got it? Now, this is very interesting, but this is even more interesting if we view this result in the frequency domain. So what we are going to do is that under the assumption of this periodicity in t, let's double Fourier transform this signal by utilizing this result. Got it? Since we have representation of this periodic signal in the time domain, we are going to use this one to find the frequency domain. So here comes the highlight like this. So this is nothing but the 2D double Fourier transform. So double Fourier transform of RT comma S. Precisely speaking, symplectic double Fourier transform. And since this was the summation of what? Some Fourier coefficient as a function of t minus s times complex exponential with a different frequency, right? Complex sinusoidal signal. Here we have what? We have again infinite sum. That's not strange. However, we have a very strange thing. But not that strange because we already know that if we have some complex sinusoidal signal e to the j2 pi f0t, then its Fourier transform is what? Something like this, having delta function. Same thing. So what you need to do is that simply just use the definition of double Fourier transform applied to this one. Then this second term automatically will give you delta function with delta located at k over capital T hertz. Got it? And this one will give you another one. So here, double Fourier transform with delta function has some effect. So let's see here. Where it is? Yeah, it's complicated. Yeah. So temporarily, the trick is that assume that the signal R of t comma s after double Fourier transform has finite bandwidth. One of the reasons why we do that assumption is I already told you, in order to develop some theoretically precise capacity or performance of some communication system, you'd better assume that signal, noise, everything is strictly band limited. And for the strict band limitedness, you'd better have some 1 over 2t odd multiple. That makes everything simple, as I told you, because you have, in that case, exactly odd number of Nyquist-Jones. But as we see here, general band-limited signal has some strange phenomena, like for some offset for vectorized Fourier transform or vector valued, matrix valued power spectral density, we have size varying vector or matrix. But anyway, so I hope you can handle that. So what we have is, where it is? Yeah, we have this proposition 4. You need to end up with this result. Ready? So the noise filtered by the receive filter W has the power, that is the integration of the quadratic form of this one. And let me tell you what is this strangely looking matrix valued function of f. Let's say xi1 and xi2 are frequency variables that you have after double Fourier transform of autocorrelation function. Got it? So this is the double Fourier transform of the cyclostationary random process. And our result already appearing here, this one, that looks complicated, but see that you have difference between xi and xi tilde equal to capital K over T. Otherwise, this becomes 0, right? So you have so-called impulse fancies. On what? On first, xi1 minus xi2 equals 0 times 1 over t. And you have equally spaced diagonal lines only on which we may have non-zero value. Actually, we have an infinite on the times some delta, but anyway. So xi1 minus xi2 equals 1 over t here, 2 over t, negative 1 over t, something like this, right? Because here, this is t, 1 over t, xi1 equals 1 over t, xi2 equals 0, right? So only on these diagonal and off diagonal area, you may have some non-zero value. Of course, on that line, you have infinitely large in terms of its magnitude, the values, but anyway. What does this mean? Remember, this is the autocorrelation function, and its double Fourier transform is somewhat believed to be, this is very dangerous. I will never endorse this interpretation publicly, but you already know that this is the interpretation of the autocorrelation function and its double Fourier transform. Got it? Remember, from here to there, what do? You multiply e to the negative j to pi xi1t and integrate over xi1. And you multiply e to the positive j to pi xi2s ds. You remember that? Now, just simply assume that S of t has Fourier transform this one, even though it may not exist in general for every sample path, but just simply assume that, okay? We may have that good property. So actually, double Fourier transform is going to give you the correlation between n with xi1 frequency component. Be careful, this and that are different functions. This is frequency domain sample path, and that is, time domain, that is frequency domain. Got it? Okay, you don't like it. So let me put tilde, okay? And tilde xi is the Fourier transform got it? View it that way, okay? Then you can understand. So this is nothing but the what? Correlation between the frequency component with frequency xi1 in n and frequency component at xi2. So this means that n tilde xi has what? Has non-zero correlation with itself only when the frequency components are integer multiple apart of cycle frequency, 1 over t. See that? Let's take some xi1, xi0, okay? Some frequency component. Now, what does the values on this line mean? N of t with frequency component xi0 has non-zero correlation whenever the frequency component has difference 1 over t apart. See that? This is exactly xi0. This is exactly xi0 plus 1 over t. xi0 minus 1 over t. Something like this. Got it? That's why I told you that cyclostationary random process has very interesting property. In the spectrum domain, it has correlation, spectral correlation. Since two-dimensional is too complicated, let me just simply draw a single frequency. And remember the power spectrum, ordinary power spectrum over random process. For a cyclostationary random process, you can derive power spectrum by using Wiener-Khinchin theorem or by using the definition. Suppose you have some power spectral density look like this. I told you in the first class meeting that a Y-sense stationary random process has no spectral correlation. What does that mean? Suppose you choose some frequency xi0, and you choose different frequencies on this support of the power spectrum. Then what happens? I showed you they are uncorrelated. Actually, orthogonal in terms of But it's in case of zero mean, they are uncorrelated. Got it? But in Y-sense cyclostationarity, what does that mean? This xi0 shifted by 1 over t, 2 over t, negative 1 over t, negative 2 over t, possibly negative 3 over t in this case. So these frequency components are correlated with this frequency component. That's explained here. Got it? Now, this is the final, already over. Then what is this single variable function? Probably you remember something like this. Suppose you have x of t, xi of t minus t0 can be viewed as delta of t minus t0, right? So you have some possibly assign different values on the height of the delta function. Now, what is this one? You define some offset f. Then you may sample here at f comma f, and you may sample at f plus 1 over t comma 0, f plus 2 over t, f minus 2 over t, f minus 3, f minus 1 over t, f minus 2 over t. And also, you can sample at these points in 2 dimensions. If signal is band limited, you will have finite number of samples horizontally and vertically, and you have a matrix, right? That matrix contains the height of this delta function at specific offset f. Now you change offset f to 0, then you sample at 0, 1 over 2, t, negative 1 over t, and these samples. If you shift f a little bit, then your sampling, let me use just this 4, changes that direction. If f is negative, the other direction. In that way, you evaluate the height of these impulse fences and put that value here. And this is the matrix valued power spectral density of a cyclostationary random process. This appears in what? In this compact form. Okay? This is 2D PSD of cyclostationary random process N over T. Got it? Okay, so we are done, I believe, with the up to this point, except the overall summation of our mean squared error, which is simply the sum of all the terms we have derived. And that can be put here. This is the symbol part, and this is the cross term. And that is what? That consists of 2 terms. First one is the noise part, and the second is the signal part, because both of them are quadratic form with the same W Hermitian and W. So they are combined here. So R is what? R is can be viewed as the 2D PSD of the desired signal plus cyclostationary interference. Okay, that's all for the day.